another topic, but it's related to clustering. Okay, so this week we talk about the clustering. So following the clustering, you can use this technique, clustering technique, to do quantization. And product quantization is a general quantization technique. So today I will give you a lecture about all the related product quantization technique, widely used in multimedia, in pattern recognition, in many areas. So this is the issues I will address in today's lecture. Okay, including the vector quantization, product quantization, and this is the abbreviation of this technique. So, and also I list the first paper about this technique. For example, PQ is published in PAMI in 2011. So it's the top one journal in computer vision. So it's already published for 14 years ago, but now it becomes a widely used technique, a common sense used in multimedia, in database, in web technique. Okay, then following the PQ and some of its derivation, like optimized PQ, is published in CVPR, and locally OPQ. OPQ is an abbreviation of the optimized PQ. And all these papers, they belong to the PQ family. And then after that, you see, in recent years, in past years, we have some papers, they use the PQ to further to use in deep learning, in language model. Okay, so I will introduce some of the such a technique use the PQ in their papers, or for example like a deep PQ, use the deep learning to learn the better product quantization, or the differential optimized PQ and disentangled representation learning. Okay, I think the main thing of this course is the approximate nearest neighbor search. So ANN search we have addressed in several weeks ago. And the ANN search algorithm actually is a trade-off among the search accuracy and among your index efficiency and also your memory consumptions, because it's a trade-off. So maybe you can give a very good search accuracy, but your index efficiency maybe will be degraded. And also, even you have a very good search accuracy and very efficient, but you have to consume a lot of memory. So it's you always have to deal with among the three issues. So based on it's case by case, based on your applications, you have to think about which one is the most important, and you have to sacrifice another one. And among these issues, the quantization is a very important technique, can be used to help your ANN search algorithm. So the quantization, if you apply it, it has some features. First, it can reduce your memory consumption. Quantization, you can regard it as like a compression. You compress your data, so actually you can reduce, so that your memory is reduced. And also speed up your index. Everything is compressed. Okay, so it can also speed up your index. But also, disadvantage is your accuracy will be degraded. Okay, I think it's reasonable. Yeah, because you do the compression, and so there are some information loss between during your compression, during the quantization. So it's reasonable that your accuracy will not be degraded. Okay, let me give you the definition of the vector quantization. Okay, so we call the vector quantization abbreviated as VQ. So basically, it tries to reduce the cardinality of your representation from your real value space by a quantizer. Okay, so in the real value space, your vector can be each dimension can be just a real value. So you can actually can be no limit. But if we give some fixed value to represent all its surrounding values, so it means we can give a fixed cardinality to represent this interval of the real value. It can be represented like this. Here, Qx is we call it a quantizer or a quantization function. So Q of x is your d-dimensional vector, x, and we will input is your vector, and then the output will be a codebook index. So the C is a codebook. A codebook can contain many code words, Ci. So suppose you have 100 code words in your codebook. Okay, so Ci will index from 1, 2 until 100. So you will have 100 code words. Also, we sometimes call code words as a centroid. So the reason is usually the code word is represented by a vector. The vector is actually the aggregation of all the vectors belong to this code word. So you can think if we apply like the k-means will build several clusters, and then you can use this vector belong to the cluster, take their mean, their average as the centroid, and this centroid we usually use it as the code word Ci. So that's why the Ci is called a code word, and we also usually call it as the centroid vector. If you use the k-means like the technique to generate the Ci's vector, you can also call it as a centroid vector over code word. Okay, and the I here, the I is the code word index, or we say it's identifier, ID, code word ID, and C is a code book, and its size is K. So it's a general representation of your quantizer Q. So the input is your d-dimensional vector, and the output is the code word. Okay, so you say a code word ID. Okay, any problem for the definition? Okay, so this vector space, based on if we use this quantizer Q, and you can imagine that your d-dimensional space is actually partitioned into k cells, and each cell you will contain several vectors, real value vectors in this cell, and all the data, all the vectors in the same cell can be represented or reconstructed by a cell centroid. So this is what we call quantization all the data in this cell, all the cluster, and we can just use the centroid to represent this data. So this data will, if it's quantized to the centroid, it's no more its original representation. It's represented by the centroid. Okay, so this is will cause the quantization loss. Okay, any problems? So we can say it's like a compression. You compress the original vector into a centroid. So all the data in the cluster will be compressed to the cluster centroid. And how to measure this quality of this quantizer? Okay, so we usually use the mean square error of the Euclidean distance. Okay, so we use the d as the Euclidean distance function, and here is the measure. The equation is placed like this. So given the quantizer, and actually is the expectation of all the data x, and is compression vector. So x is the original vector, and the q of x is the quantized vector. So we can calculate their distance, use the Euclidean distance to compare their distance between the original one and the compressed one. And take the square here. Because it's expectation, it can be formulated as the integral like this. Calculate the probability of x and time with the distance between the quantized vector and the original vector. Okay, any problems? So based on the mean square error, so there is called a Loic condition, optimal conditions for the quantizer Q. So there are two key points. That first, if x is quantized to its nearest centroid, so if the original data x is quantized to its nearest centroid, so it's like the k-means process, right? So all the data has to find its nearest centroid, and so that it belongs to the cluster. Okay, so all the x is quantized to the nearest centroid, and the second point is the reconstruction value means the centroid, the cluster centroid must be the expectation of the vector in the Bernoulli set. Okay, so this means all the data belong to the centroid, belong to the centroid, belong to the cell. So the centroid should be the average, the expectation of all the data belong to the cluster. So it's also another step of k-means, right? So k-means we have to, after we do the assignment of each cluster, and then we will recalculate the centroid of the cluster by using all the data in the cluster, right? So just remember, just recall the process of the k-means. So x should be quantized to the nearest centroid, and the centroid should be calculated by the average, the expectation of all the data assigned to the cluster. And so based on this, you can say we can find the best compiler Q. Okay, so all this process can be done by k-means cluster. But you have also reminded that k-means cluster is local optimal. It's not global. But you have the chance to achieve or very approximate to the global optimum. Okay, any problem? Okay, so we can smoothly connect better quantization by using K-means. Okay, so just recall the class we have learned in last 2 weeks. Okay, so just apply the K-means, you can get the centroid and get the cluster assignment of each vector. Okay, and then next we can also use this information to build up an inverted file-based index structure. So let me give a detail about how to build up the inverted file index. We abbreviate as the IBF. So the IBF, this is the index structure. So it's widely used in information retrieval, in database structure. So here is our database. Okay, so in this database we have n data. There are d-dimensional value, d-dimensional vector, real valued vector. Okay, so you see there are several points just in the d-dimensional space. And here we already applied the K-means to separate to divide the d-dimensional space into several cells. We call it the Barnoy cells. Okay, so you can see this is comes some irregular region to form each cell. So, and for each cell, we will build up and we call it the inverted file list here. This list just keep all the data located in this region, in this cell. So for example, X4, X9, X16, all these data, they are located in this cell. So we build inverted list file here. Okay, so all the cells, each cell, we will build a list file for it. So we call this structure as an inverted file index. This file structure can help us to accelerate to speed up your search speed. And also we will build up a table called a codebook. This codebook just keep a record about your the index, the central index, and also its vector. So for example, C1, suppose it's this one, is the central of this cell. We will keep a number, ID. Okay, it's the C1, means it's the first region. Okay, this is the first central. And its vector can be calculated by just average all the original vectors stored here to calculate the centroid. And the centroid is also a d-dimensional vector. So we can store in this code. So we just store all the here. Suppose we have 7 cohorts. Okay, so we store the 7 cohorts along with together with the vector, the centroid vector. And we call it a cohort. Okay, so that's all. So if you build an inverted file index, you have to build up the code and also the inverted file. All of this you have to store in your memory. Okay, any problem? And after it, and if we perform a search in this inverted vector Q, and first we have to compute the distance to all the co-centroid. Okay, so we have here we have 7 centroids. So the query vector has to compute the distance between all the cohorts, and to find which cohort is closest to the query. Suppose that maybe C1, this one, is closest to the query Q. Okay, so we will go to its emerging file list, and here we have several vectors stored here. Right? We can treat them as candidates. So the Q will compute the Euclidean distance with all the candidates, and then we can sort them to return to the user the top K result to the user. Okay, any problem? During the search process, you can use the IPF structure to accelerate the search process. You don't need to search all the data stored in the file structure. You just need to find which cluster, which centroid is closest to Q, and we only search the file list associated with the closest cluster. Okay, so here the search parameter will be the number of clusters to inspect. So it means maybe you should not only find the top 1 cluster, maybe you should find the top 2, top 3 clusters, yeah, to reduce your search error. Yeah, because there's a quantization loss. So all the data is represented by your centroid. So if you only based on the distance between the query and the centroid, it's not very accurate. So maybe you should consider not only top 1 cluster, maybe top 2 or top 3 clusters, and then inspect all their emerging files. Okay. It can increase your accuracy, but also it will increase your search time. Okay. It's again a trade-off, right? And the number of candidates you have to inspect. Here is we call it a candidate. This list is a candidate. They are very close to the query, so you have to inspect all the data, all the candidates stored in the cluster. Okay, so it's a general description about vector quantization. And next, we'll talk about product quantization, PQ. So PQ is a general vector quantization technique. You can treat VQ is a special case of PQ. Okay, so I will let you know why, according to its definition. Okay, so first, let's start from why PQ is developed. Okay, the idea is if we want to reduce the quantization error, what is the best way? You can use more centroid. Use more centroid, and you can effectively reduce your quantization error, right? Because think about if you use only 10 clusters, and on the other hand you use 100 clusters. So which one can give you a better, a smaller quantization error? 100, right? because you use 100, so you will generate more centroids. And each centroid you can partition the space into a smaller space. So actually it can reduce your quantization error. If you use only 10, your region will be large, right? Each cluster contains large area, and it contains more data, but it produces more quantization error. Okay, it's very reasonable. So using more centroid can reduce your quantization error. Okay, here let's consider we have 128 dimensional vector, like the SIFT data set. And okay, so if we think we want to use more centroid, can we use centroid, the number of centroid like 2 to the 64? Is this possible? Okay, so actually the number of the centroid is 2 to the 64. It's very large, right? I think it cannot be represented. Can be represented in your computer. Even in a server level computers, it cannot be represented. It's too huge, right? Okay, you cannot enumerate each one. It cannot be calculated. It cannot be used. And so, if we want to generate 2 to the 64 centroids, can we use Chih-Yi's cluster? No, impossible. It cannot run. But PQ can do it. You can use PQ to achieve this goal. Okay, so PQ is why they developed it to try to solve this issue. It can produce a large set of centroids. How to do it? You just divide your original data space into several small space, subspace. Okay, the idea is this. So the d-dimensional vector X, we can split it into n subvectors. They are distinct, no overlap. So you see there's we have it's a little funny, but okay. So you see this is the first one, second one. First one, the first subvector, and the second is the less n, the n subvector. So each vector, each subvector, we will use a quantizer to do the quantization. So in total we will have n quantizers. So here is the representation like this. So you have PQ quantizer like this. So U1x means is the first segment, first subvector of x, and the UN of x means the nth subvector of x. And for each subvector we use the corresponding quantizer. It's a Q1. It's what is used for the first subvector. And then Qn is a quantizer used for the nth subvector. So you can imagine that we just divide it, the original d-dimensional vector, into n subspace, and each subspace will have also built up a quantizer for it. So here are some notations, like the d star here means we divide the original dimension d into n segments. So each subspace now is dimensions d star. And the Qj is the subcompiler of the jth subvector. And here, the codebook now is not only one codebook. So remember, in K-means we just build one code, right? But now here we have n subspace. Each subspace has its own code book. Okay, so now we will have C1 until Cn. We have n code books, and because the total code book is a product of all the subspace code book. So from C1, suppose you have 10, and you have 10 code books, and the C2 also 10, C3 also 10 until n. So you just time all of them, you can get a very huge combination of your code book. Okay, so here, so suppose each subcompiler has a k star central, and because you have n, so each one you have k star central, k star cowords, and you have n code books. So the total cowords you can generate just by combining them together, and combine them together, and the total central is denoted as k to be the k star to the nth. K star is the number of cowords in each subspace, and n is how many spaces here. So you can generate so many central by using the PQ. Let me give you an example. So here, check the left-hand side. Okay, this is a code book. This code book is here only n is the number of the partition. So we have only one partition, and the dimension is 128. So this means we don't apply any partition on your dimensional space. Okay, so we can apply the k-means directory, and here we generate how many? 65,536 total total central is here. So each core we just keep is 128 dimensions as the central. Okay, this is the code, and we can calculate this code size. The code size is like this. It's k is the number of your central, and d is your dimension of the central vector dimension. And each dimension we will use 4 bytes to store it. So the total. So the total size you have to keep the code book is about it's 33 megabytes to store this code book, and this code book contains more than 65,000 central. Okay, and on the right hand side, this is here we use the PQ, and this PQ here you see we divide your space into 4. So you see we divide the space into 4 segments, and each segment will be 32 dimensions. Okay. And then you can see because we divide it into 4 segments, each segment here we use only 16 centroid. So you see we have a 16 centroid for the first segment, and for the other segment we also have 16 centroid. So this can be easily done by just separate, divide into four subvectors, And this subvector in ground it means here k is 16. So you can generate 16 clusters. Okay, so based on this, how many central you can generate? Here, 16. And the second is also 16, 16, 16. You have 16 cores when you combine them together. In total, you will have 13 to the 4th. You have the same this, right? We can generate the number of the centroids as the same. It's 65,000 centroids. Okay, any problem? But what is the corpus size? The corpus size is calculated like this. The K star is for each subspace there are 16 centroids. So K star is 16, and the E divided by N is the length of the subspace. And because you have N segment, 1, 2, 3, 4, I have 4 segments, and each value I use 4 bytes to represent it. So it's the total size of the code in PQ. So the calculation will be this. The size used is about just a little bit more than 8,000 bytes. Compare with this. We all have the same number of the central, right? But the code size stored in memory is 33 megabytes. It's only 8K bytes. Much smaller, right? So this is the main power of the PQ. If you want to generate the same size, the same number of the central, your memory use is very compact. And then you can use the idea to generate more. So if you want to generate 2 to the 64 central, how to set up? You just need to set up your N, your number of segments, and each segment, how many centroid you will use. You just need to determine these two. Then you can calculate. You can enumerate how many centroid use in your application. Okay, let me show this figure. In these figures, the x-axis is the code length. So you can treat the code length, which is 64 bits, this means you can generate 2 to the 64 centroids. And here you see these two methods and these two parameters configuration they can achieve. Yes, 2 to the 64 centroids. How to do it? Let me show you the configuration. First, we check the green line. The green line, you see the K star. K star is the number of centroids in each subvector. Okay, so from the 16, 64, and 256. Okay, the green line is 8. N is 8. So it means the segment, the original space is segment into 8. 8 segments. And each segment we use 256 centroid. Okay, so with this configuration, how many centroid we can get? The total centroid. Okay, so you have each subvector you have 256, right? So it's actually 2 to the 8, right? Each segment. And because we need to be the total central by combining all the segments together. So this is the first segment, this is the second segment. Total you have 8 segments. Right? Each segment you have 256 central. I mean the green line. This green line. Yeah. So it's total in total is so this is why we can get 2 to the 64 central. And the black line shows another way. The black line shows another configuration too. We can also get the 2 to the 64 centroids. So you can see the black line is dividing the dimension into 16 segments. Okay, so we have each segment. Here we use this one is K star is 16. So we have 16 segments. Sorry, 16 and 16 central each segment. Right? And we have totally we have 16 segments. So result is so again we can generate 2 to the 16 for central. So any problems? You can use here. I just show you use the 2 different configurations to generate 2 to the 64 central. And which one is better? You think? If we think the better one should be it should be the smaller foundation error. So which one can generate a smaller foundation error? Black line or green line? Which one? Under the same colors. Yeah, should be green one, right? Because this figure just show you the information. The y-axis shows the distortion. Okay, show the distortion here, the lower the better. So you can see even they are all they have the same colors, they have the same size of the central, but green line is better. Okay, you can check all the others. So for example, this one is 32 bits. Means I want to generate, if I want to generate 2 to the 32 centroids, okay, you can use this configuration or this configuration. But this one is I segment into 4. I segment the dimension into 4 segments. This can generate a smaller compared to this. This one, the foundation error is smaller. So it gives you a suggestion that if you fix your collects, okay, and then you should use less segments, but each segment you should use more centrally. Use this combination to generate your central. Okay. Any problems? 4 segments. In each segment, we use 256 centroid. But if you use this, you have 8 segments, and each segment has 16 centroid. The distortion will be larger than this one. Okay, use less segment, but each segment use more centroid can reduce your quantization error. Okay, any problems? Okay, so we stop here and take a break.